In this video, we will explore the fascinating reasons behind scientists' conjecture that CERN has managed to open a portal to an additional dimension, taking us to a whole new level of understanding of the cosmos. We'll discover the surprising research and results that support this idea, as well as the exciting implications this could have for our knowledge of the universe. Get ready to embark on a fascinating journey into the unknown in the confines of CERN and its potential door to a dimension beyond our imagination. Number 1. Scientists get involved in a lot of things that can easily get out of control and get them into trouble. Our magnetic field has been put under pressure by an experiment carried out by certain scientists. Earth's magnetic field opened up after the Large Hadron Collider was turned on, leading to a totally unexpected result. Magnetic monopoles may not mean much to the average person, but scientists are deeply interested in them because of the effect they could have on the universe. That's why scientists spend a lot of time looking for these strange objects. But where did the idea of a monopole come from, and what could be the effect of monopoles on the universe? However, no matter how small you cut a permanent magnet, you would never end up with a North Pole or a South Pole by themselves. In other words, the magnetic charges only came paired in a dipole configuration. Several discoveries made during the 1800s helped us understand the electromagnetic universe. We learned about induction, which is the process by which moving electric charges generate magnetic fields, and how changing magnetic fields, in turn, induce electric currents. We also discovered electromagnetic radiation and how accelerated electrical charges can emit light of varying wavelengths. We discovered that the universe is not symmetrical in terms of electric and magnetic fields. Maxwell's equations only contain electric charges and currents, but by adding the ability for objects to also possess a fundamental magnetic charge, they become completely symmetrical. This means that induction now works in the opposite direction, and that a changing electric field can induce a magnetic current, causing magnetic charges to move and accelerate in a material that carries magnetic current. For a long time it was a speculative idea until we recognized the role of symmetries in quantum physics and nature. Electromagnetism could be symmetrical between electrical and magnetic components at a higher energy level, and we live in a low-energy broken version of that symmetrical world. Paul Dirac showed that if there were a magnetic charge anywhere in the universe, it would quantumly imply that electric charges would have to be quantized everywhere, even in fractions for quarks. The discovery of a mechanism that could explain why the universe has the properties we observe is a powerful clue to new discoveries in physics. Scientists are still searching for magnetic monopoles, although their existence isn't proven. When scientists investigate a theoretical idea, they look for pathologies, or reasons why the universe might break apart because of that idea. When considering the magnetic monopoles proposed by Polyakov, a pathology was found that could cause the universe to collapse. During the early universe, any particle-antiparticle pair you can create with enough energy is created when the symmetry is broken. If given non-zero mass or many massive particles are suddenly added to the universe, the energy density increases rapidly and the universe collapses. Therefore, although magnetic monopoles could exist, it is important to continue searching for them while investigating their possible pathologies. Scientists have been searching for magnetic monopoles, and although there is no evidence of their existence, they have not given up their search. When Polyakov monopoles were proposed, pathology was discovered suggesting that magnetic monopoles could close the universe, which could have disastrous consequences. This is known as the monopole problem and is one of the three main drivers of cosmic inflation. Scientists have used cryogenic experiments to search for magnetic monopods, such as Blas-Cabrera's experiment in 1981, which produced a signal that could have been caused by a magnetic monopole. Although there is no conclusive evidence for the existence of magnetic monopoles, cosmic inflation could solve the monopole problem as long as the universe does not warm above the grand unification scale after inflation ends. Experiments were conducted to look for magnetic monopoles after Cabrera's experiment, but no one else found them. Still, CERN has been passionately searching for magnetic monopoles with the Large Hadron Collider, LHC, which is the world's largest particle accelerator. The LHC fires high-energy particles that collide at speeds close to the speed of light, producing a complex shower of other particles. Scientists rely on two highly complex detectors, like ATLAS, to track these particles and see the fundamental building blocks of our universe. The ATLAS helped in the discovery of the Higgs boson. ATLAS is a detector that is half the size of Notre Dame Cathedral and twice the weight of the Eiffel Tower in Paris. Scientists use ATLAS and other detectors to investigate science fiction topics, such as other dimensions, unifying forces, and dark matter. ATLAS and CMS are the only detectors dedicated to solving the mystery of the Higgs boson at the LHC. During the particle collision at the LHC, particles collide 600 million times per second, providing valuable information for understanding the internal forces of the atom. Detectors like ATLAS can't record all the information they see. During reconstruction, scientists compare computer-simulated collisions with real collisions to test their theories about particle behavior. The data center processes 1 petabyte of data each day, which is equivalent to 223,000 DVDs. However, scientists can only record a small amount of data, making new science difficult to find due to the large amount of information they must sift through. A group of imperial physicists have devised new experiments at CERN's Large Hadron Collider, LHC, that produce conditions more conducive to the creation of monopoles. Although no evidence has yet been found for their existence, experiments allow researchers to fine-tune the likely properties of monopoles and rule out the existence of certain types. Furthermore, these experiments have given a much better idea of where the search for monopoles may be headed. In 2018, the LHC collided lead nuclei, producing the strongest magnetic field in the universe. These magnetic fields could produce north and south monopoles, according to the theory of the Schwinger mechanism. Although no evidence of monopoles was detected, the organization made an unusual announcement. A crack in the Earth's magnetic field appeared and remained open for almost 14 hours. The crack was due to a co-rotating interaction region, CIR, from the Sun, a large-scale plasma structure. CIRs are ejected from the Sun toward Earth and can contain shock waves and compressed magnetic fields, resulting in stormy space weather. Coronal mass ejections, CMEs, are also ejected from the Sun toward Earth and can contain shock waves and compressed magnetic fields, resulting in stormy space weather. Solar flares are caused by the realignment of the Sun's magnetic field, which produces CMEs. CMEs are most common during solar maximum and can cause technological failures. For example, the Carrington event in 1859 disrupted the global telegraph system. CMEs also produce beautiful auroras, but they can be destructive. The largest CMEs can fill almost a quarter of the space between the Earth and the Sun when they reach our planet. CMEs can cause chaos on Earth by generating electrical surges that overload power grids, causing blackouts and affecting radio communication. GPS systems and orbiting satellites are also vulnerable to CMEs and can be damaged or knocked out of position. In 1989, a CME caused a 12-hour power blackout in Quebec, Canada, causing at least $10 million in damage to Quebec's power company, Hydro-Quebec. Space weather can cause damage to satellites and communication systems. In 2020, a geomagnetic storm destroyed 40 SpaceX Starlink satellites, valued at more than $50 million. The magnetic field was believed to provide quick protection from solar storms, but it is now known that they remain open for hours. A magnetic shield can absorb the force of space storms, but some of the energy escapes and causes problems with systems. It's like a house with an open window during a storm that deflects most of the storm, but can destroy the couch inside the house. The Sun is entering an active period and the chances of seeing auroras are good. However, there is reason to worry about the effect on Earth's magnetic field, as the Sun's solar wind can be so powerful that it can strip gases from the atmosphere and cause the loss of atmosphere and water on a planet. This is what likely happened on Mars, where its atmosphere and water were swept into space when its magnetic field disappeared. Without Earth's magnetic field, our atmosphere, oceans, and life would perish. Many animals, including birds, sea turtles, lobsters, bees, salmon, and fruit flies, use the magnetic field to navigate and find their homes. If the magnetic field disappears, these animals could lose their navigation ability, which could endanger their lives and lead to the extinction of many species. Number 2. Observation of unexplained phenomena. The Large Hadron Collider, LHC, at CERN is the most powerful particle accelerator in the world. At its core, the LHC is a 17-mile ring buried beneath the French-Swiss border near Geneva, where subatomic particles travel at nearly the speed of light. The LHC allows physicists to recreate the conditions that existed a fraction of a second after the Big Bang. During the initial stages of operation of the LHC, several unexplained phenomena were observed that baffled scientists. For example, detectors at the LHC began recording an unexpectedly high number of particle collisions at certain energy levels. These anomalous events did not match predictions based on the standard model of particle physics, which has been the cornerstone of our understanding of the subatomic world for half a century. Experiments called beauty experiments were carried out to measure the decay of beauty quarks, elementary particles. The results showed discrepancies with the standard model, indicating the presence of new, unknown physics. Anomalies were also observed in the behavior of neutrinos, particles that interact minimally with matter. The OPERA project at CERN detected neutrinos that apparently traveled faster than light, challenging Einstein's theory of relativity. Although it was later attributed to a technical glitch, these observations sparked debate about the possibilities they might imply, including the existence of extra dimensions. The LHC experiments yielded heavier than expected Higgs bosons, suggesting the possibility of interactions in higher dimensions, which could indicate the existence of dimensions beyond the conventional three spatial dimensions. The weakness of gravity compared to other fundamental forces has also generated uncertainty, and it has been proposed that this weakness may be the result of its dispersion in multiple dimensions. Although no conclusive evidence has been obtained for the existence of extra dimensions, these phenomena challenge our understanding of fundamental physics and raise questions that the standard model cannot answer. Therefore, scientists consider that these mysteries could be the gateway to discovering a completely new reality, possibly thanks to the giant collider at CERN. Number 3. Particle acceleration and other dimensions. Particle acceleration at CERN is key to research to reveal the mysteries of the universe. Experiments conducted by colliding particles at high energies offer intriguing clues about the existence of additional dimensions. These experiments seek to understand the fundamental blocks of matter and their interactions. The high energies achieved at the LHC make it possible to recreate extreme conditions of the early universe. In these intense collisions, possible extra dimensions are explored, according to theories such as string theory, which suggest the existence of more than the three known spatial dimensions. If extra dimensions exist, they are expected to be compacted to very small scales, not directly accessible in the current experiments. However, particle collisions at the LHC could generate enough energy to briefly unfold these dimensions, offering a fleeting glimpse of their existence. The existence of extra dimensions may imply the presence of new particles called Kaluza-Klein modes. These hypothetical particles would be generated from additional quantized dimensions. In collision experiments, the extra energy could produce these elusive particles, leaving traces detectable on CERN instruments. Furthermore, known particles could be affected by the extra dimensions, showing anomalies in the energy or momentum observed in collision events, which would indicate leakage of particles into those extra dimensions. The detection of these anomalies has fueled speculation about the existence of extra dimensions. On the other hand, the study of particle disintegrations can also provide information about the presence of extra dimensions. These decays could show deviations from the standard model due to interactions with the additional dimensions. Scientists closely analyze the decay products in search of anomalous patterns that could indicate the influence of extra dimensions. Although direct evidence of extra dimensions has not yet been found at CERN, the high-energy collisions and measurements made offer intriguing clues that cannot be fully explained by the standard model. These experimental results have led scientists to believe that the exploration of extra dimensions is within reach. The quest to understand the true nature of our universe continues, fueled by particle acceleration and the possibility of discovering a portal to another dimension at CERN. Number 4. Quantum entanglement experiments. Quantum entanglement is a fascinating phenomenon in which particles are inseparably linked regardless of their distance. Quantum entanglement experiments at CERN help us understand the possibility of opening a portal to another dimension. In these experiments, non-locality is investigated, where the state of one particle is instantaneously related to the state of another, even if they are separated by enormous distances. This behavior challenges our understanding of causality and suggests that information can be transmitted faster than light. At CERN, scientists are conducting experiments to explore the limits of quantum entanglement and its connection to additional dimensions. They entangle particles in the laboratory and separate them over large distances to test how far entanglement can extend, investigating whether entangled states can exist in dimensions beyond the conventional three spatial dimensions. Quantum entanglement experiments at CERN study entangled particles and look for correlations in different dimensions. These experiments explore the spooky action at a distance described by Einstein, investigating whether extra dimensions facilitate an instantaneous interaction between entangled particles. Although a direct portal to another dimension has not been discovered, these experiments provide insights into the nature of reality and hidden dimensions. The connection between quantum entanglement and extra dimensions challenges our understanding and could lead to discoveries that change our perception of the universe. As scientists continue to investigate, they hope to find clues to an elusive dimension beyond our reach. Number 5. Microscopic black holes and their implications. The possibility of microscopic black holes, tiny versions of their massive counterparts, has intrigued scientists and sparked discussions about their implications for our understanding of the universe. In this chapter, we delve into how the study of microscopic black holes at CERN provides insights into the existence of additional dimensions and the possible opening of a portal to another dimension. According to certain theories, such as string theory, the existence of additional dimensions could lead to the production of microscopic black holes at the energies achievable at the LHC. These microscopic black holes would be incredibly small, with a size on the order of the Planck length, and would quickly evaporate due to Hawking radiation. Detection of these elusive entities would provide strong evidence for the presence of additional dimensions. The creation and potential detection of microscopic black holes at the LHC has sparked debates and concerns among both scientists and the general public. Critics have raised questions about the safety of producing such small black holes, fearing they could grow uncontrolled and pose a risk to Earth. Proponents argue that Hawking radiation emitted by microscopic black holes keeps them safe and provides information about gravity and spacetime. The formation and evaporation of these black holes allow gravity to be tested in additional dimensions. Studying the decay signals of these black holes could reveal clues about the extra dimensions and generate signals in CERN's detectors. Although there is no conclusive evidence that microscopic black holes are portals to another dimension, their research demonstrates scientists' dedication to unraveling the mysteries. We are getting closer and closer to the possibility of discovering a portal to another dimension through these microscopic black holes. Number 6. The Higgs boson connection. The discovery of the Higgs boson, a fundamental particle that gives mass to other particles, was a monumental achievement at CERN. The Higgs boson was first observed at the LHC in 2012, confirming the existence of the Higgs field and providing a missing piece to the standard model of particle physics. This particle plays a crucial role in our understanding of the fundamental forces and particles that make up the universe. However, the properties of the Higgs boson and its interactions with other particles also offer clues to the potential presence of additional dimensions. According to models with additional dimensions, the Higgs boson could be influenced by interactions in these hidden dimensions, which would modify its properties compared to the standard model. Scientists carefully study the properties of the Higgs boson to look for deviations that indicate the existence of additional dimensions. By measuring its mass and analyzing its interactions with other particles and fields, scientists are investigating the possible influence of extra dimensions on the Higgs boson.